to deliver a talk in this series. So,
Okay.
Andrei Dmitrievich is distinguished among the most eminent theoretical physicists. He led to the paradigm shift not only in theoretical physics but also in the sociology of science, I must say. Before inflation, actually, I remember from my Moscow State University days that cosmology was not considered to be the part of physics. So it takes me back to my Moscow State University days. I would like to say a few words that after graduating in 1978, I joined Moscow State University, joined Professor Feinberg for PhD program, Department of Quantum Theory and High Energy Physics. And Valery Rubakov also graduated same year from Bogolubov department. And next to our department, father of modern cosmology, Zildovich used to teach 1 year course on evolution, structure and evolution of universe. He was a remarkable teacher. But to the best of my knowledge, none from our department went to attend that lecture because cosmology was not considered to be a part of physics at that time. Actually, it is all inflation did lot to it. And at that time, there were very few who understood the importance of cosmology. It will not be wrong if I say that most of them were in USSR. Well, perhaps it is related to the history. Yevgeny Lifshitz, as early as 1946, analyzed and classified cosmological perturbations as scalar, vector, and tensor perturbation that we know today. So, in the in Lebedev Institute at that time, there was a wonderful physicist. Actually, these are not my words. The Feinberg, my guide, would say, David Veliklevny physics. David is a wonderful physicist. And in 1970, can you imagine? 2 years after formulation of electroweak interactions, Kirchnis was thinking about spontaneous symmetry breaking of electroweak symmetry breaking as a cosmological phase transition. So in 1971, Andrei Dmitrievich graduated from Moscow State University and he joined Kirchnis for PhD. He went to a right person in right time. It was his vision. So he did that. I suppose they took few years, maybe 4 years, to realize the electroweak phase transition, electroweak symmetry breaking as a first order phase transition. In this scenario, they could have a prolonged state of exponential expansion of universe dubbed inflation later. But this scenario had certain very important issues. The you know that first order phase transition proceeds always through bubble nucleation. So in 1978, Andrei Dmitrievich with Gennady Chibisov demonstrated that the collision of vacuum bubbles gives rise to strongly inhomogeneous universe. Probably that was the reason they might have for time being abandoned the scenario. In 1988, Alan Guth used the same scenario, same idea to address the shortcomings of hot Big Bang. But the problem of bubble collision remained, and it was resolved by Andrei Dmitrievich first in his paper on new inflation, and finally in his seminal paper on chaotic inflation, which was written in 1981 but published in 82. In the same year, 1981, Chibisov and Mukhanov analyzed the and evolved or analyze the cosmological perturbation in the context of Stravinsky model. So the name that I have mentioned, these are those names from USSR who shaped the modern cosmology you know. Now I am tempted to say the following words, which are not my words, which were repeatedly said after inflation was discovered. These are the words which were repeatedly said in Moscow State University, and that cosmological phase transition turned out to be a lucky one for Andrei Dmitrievich. It led to a first order phase transition in his personal life. Namely, it got him the attention of a brilliant, beautiful girl, Renata Keller. Renata Keller is a brilliant physicist, theoretical physicist who completed the first order phase transition, who completed the renormalizability of electroweak interaction after the
Yeah.
paper of Weltman and Hooft. So, and these are not my words, but I have repeatedly heard. I repeatedly heard many, many things. I don't have time to say everything here about Andrei Dmitrievich. So, Andrei Dmitrievich received all important awards and honors for his contributions. I wish him the Siberian health, as the Russians would say, and wish that the final recognition, you know what do I mean? That this final recognition I wish comes to him as soon as possible. With this, I request Andrei Dimitrievich to tell us about his reverse engineering of the universe.
Okay. I'm very grateful for such a detailed and very accurate presentation of many things that happened in cosmology many, many years ago. And in fact, I start with uh, describing inflationary theory from the moment when it was proposed. And I will try to explain why this theory um, really was desirable. And also, I will talk about some changes which this theory resulted related not only to cosmology, but in part to string theory. So we'll see. So first of all, this is the picture. Do you see it clearly now?
Yes.
Oh,
Sorry,
okay.
Professor Linde, is it possible for you to go full screen?
Oh, yes, I can do it. Okay.
Excellent.
So, so this picture in the left medium part, you will see the Big Bang and then inflation. And it's a very interesting question. What was first, Big Bang or inflation, or it was the same thing, or maybe something else? So let me try to explain the way how I see it, even though we still don't know. It's only 45 years, since the time when this theory was proposed. So why do we need inflation in general? And to understand it, I will start with a simple picture of the Big Bang. So something banged, and what we see right now that galaxies are moving away from each other. The paradoxical thing is that if we would live very, very far away, not at this planet Earth, but very far away, then at some different galaxies, I would also see galaxies moving away from me, and that's because just the space expands, and therefore everything moves from any place where the person make an observation. This was such a shocking, well, uh, actually there are so many shocking things about cosmology that when you try to understand how is this is the world where I live. So this was this explosion because the space was expanding and we see it, and now we are trying to understand where all of this came from. And for that, we may play the movie back in time. Okay, so forward in time, the universe expands. Back in time, the universe becomes smaller, smaller, and smaller, and all of these galaxies move close to each other, and particles close to each other. What happens when you have photons in the box? When you compress the box, then you compress the wavelength of the photon, and the energy of a photon is inversely proportional to its wavelength. So its energy or temperature of the photon gas, it's inversely proportional to the size of the universe. The universe is large, temperature is small. The universe is small as it was in past. The temperature was large. So it looks like it is inevitable that if I see photons flying in cosmic microwave background radiation right now, then previously they were much more energetic, much more blue, ultraviolet, X-rays, whatever. And first moment, this Big Bang where everything was created. So that was the standard Big Bang theory. And everybody were, well, pretty happy about that. But there were some issues about this, some philosophical issues, and physicists they have natural explanation. Let's just do mathematics, and so we were all doing mathematics, and philosophical issues were some kind of aside. But then people started thinking about it. So, oops, let me try to move it. Let me see. Oh, yeah. Okay. So let's return to very early stages of the universe, where the universe was very, very dense, temperature was very large, and what we know that we cannot just easily go all the way back to the singularity, because when the energy of photons or energy of any other particles becomes comparable to Planck energy, or temperature becomes comparable to the Planck temperature, which is the same energy, Planckian temperature, or time close to the Big Bang becomes very, very small, and density becomes greater than Planck density. All of these things happen at the same time. I cannot go beyond that point because quantum gravity corrections become so large, quantum fluctuations become so large that whatever I say, it would be completely unreliable unless maybe string theory will teach us how to deal with this, or loop quantum gravity can teach us whatever. So we're still learning. But the idea was we come to this Planckian density, and from that point, at least we can describe the universe using normal Einstein gravity. Well, so if so, let's start with this moment. And it's a convenient system of units where you measure everything in Planckian units. So gravitational constant is equal 1, speed of light equal 1, and then density at the Planckian time was also equal 1. But this one, Planckian density, is actually huge. It's 10 to the 94 something grams per cubic centimeters. And if we combine all matter which we see right now, put it to this point of Planckian. So what's interesting is that when we just count everything that we can see now, we do not see everything. We see at a distance which is proportional to the age of the universe multiplied by speed of light. It's a little bit larger than just speed of light multiplied by age of the universe, but that's a separate issue and it's just some factor. But this is what we see right now. We count all particles available right now. And it happened that the total mass of the universe right now is approximately 10 to the degree 50 tons. Okay? So it's not a billion tons, not a billion tons. It's the number of 10 to the 50 zeros after this, 10 to the 50. Huge, super heavy universe. And the question is, how is that? There was nothing, and then boom, and you have these 10 to the 50 tons. No, 10 to the 50 tons is what we see now. And previously, the universe was much heavier because each photon right now, it was compressed and its energy was larger. And well, estimates, which I just checked before, while preparing to this lecture, that the total mass of the universe was approximately 30 orders of magnitude heavier than this 50. It was heavier, 30 orders of magnitude. So it was 10 to the 80 tons of something exploding. And there is another interesting thing about it. Well, if you uh, go back to this point, at this time, at the Planckian time, uh, particles of light can travel at a distance which is proportional to speed of light multiplied by time. So everything is in units of one. At that time, light was capable of flying to the distance equal 1 at this stage. And one can calculate how many particles would be at this small part of the universe of a size 1. So time 1, speed of light 1. So inside this light cone, how many particles I would be able to see at Planckian density? And the answer is I would see one particle, maybe 2 or 3 particles. So this horizon of visibility would be extremely small, not 10 to the 90 particles, which I see right now, 10 to the 90. Oh, that is all particles which we see now. It does not mean that it's all particles in the universe. The universe may be much larger. But what I can see, small portion, right now contains 10 to the 90 particles. But at the Planckian time, it contained 1 particle or 2 particles or 10 particles maybe, okay? Because our definition of what Planck time is not precise. But this means that, imagine that I want to create the universe. Well, of course, it was done without me asking, but I'm trying to figure out, like, people are making models of airplanes. Is it possible to build something looking like a universe? So at the time when the universe just emerged, I was able to control only 1 particle because everything else was causally far away from me. I could not influence it. And this means that, well, I could not be a god. Okay, so I could not make all of this. And therefore, the question is, how is that? Where all of these particles came from? Why, if I look to the right of me, I see galaxies, which, well, it is at the distance 14 billion light years away from me. Okay, and another galaxy 14 billion years to the left of me. So these 2 galaxies are at a distance 2 times multiplied by 10 to the 14 billion light years. And this means that people at the left galaxy cannot see right now people at the right galaxy because it takes twice as much time for them to see each other. I see them, but they don't know anything about each other. How is that the density of the universe to right of me and to the left of me is the same? So that is one of the issues which inflationary theory wanted to address. And the idea of inflation most easily understood when you compare it with the standard Big Bang story. So standard Big Bang story looks like that. I already told you one aspect of it. Here is another. Take a box containing 1,000 of protons. Now, it's a part of the universe. It expands together with the universe, and it becomes large. Like it grows 10 times, 100 times. How many protons in the box? And the same number of protons. That was the assumption of the standard Big Bang physics. The total number of particles in the universe practically does not change. It exploded, universe, and then total number of particles from the very beginning to the very end. No, maybe it was grown because of some non-equilibrium processes. Maybe it was grown 10 times. But basically, when we have 10 to the 90 particles, then it maybe 10 to the 90 became 10 to the 91. So it is not very substantial. So that was the idea of the Big Bang. You have the same number of particles in the beginning and in the end. And the total energy in this box can only decrease. Why decrease? Because photons become long and longer and longer wavelengths, they lose energy. So expansion of the universe from the point of view of energy is a losing proposition. The total energy of the universe always decreases. So that was one of the questions which was bothered Zildovich. How is that the universe can only lose what it has? So then you may start with the maximal something and where this all came from. And now the way how you can understand it from the point of view of inflation, but here is a list of the questions which we're trying to answer when inflation theory was proposed. What was before the Big Bang? Why the universe is so uniform? Why it is not exactly uniform? Because here are galaxies. Why it is isotropic? Means that it does not rotate like a hole, does not look like a ballerina, doesn't look like you have one axis, or at least no clear axis. So why is it so? We have galaxies rotating, so it would be natural to expect that our universe is rotating. why all of its parts start expanding simultaneously, why the universe is flat, why is it so large. And what happens is that some of these questions, the first one, what was before the Big Bang? We do not even know whether this question makes sense, and that is a separate issue. But all other questions we were able to consider, and they were either completely or partially, or at least to my own satisfaction, solved by inflationary theory. So that's why we study inflation, and that is the main idea qualitatively of inflationary theory. Now, I am going to cheat a little bit. I cannot be totally honest because this is something about which I will say this is where I was cheating. But let's first make this cheating part. So suppose that you have a box with heavy vacuum. Now, this is not cheating yet. This is what we find right now experimentally. Cosmologists made observation, found that energy of vacuum right now is very, very tiny, but not zero. So once you learn that it is possible, so we may also consider a possibility what will happen if the energy density of vacuum is large. So this is not cheating. This is honest to God physics. It's possible. Then, oops. Then the universe starts expanding, and this vacuum remains vacuum. So what's vacuum? Nothing. Energy density of nothing is the same. Here the universe didn't expand, here it is expanding, but it's the same nothing. So if this nothing was heavy, if this nothing has this property of having energy density, then the same energy density is in the large box. And this means that when the universe expands, total energy of the universe starts growing. Okay, so that is the first thing which looks very, very strange. But then let's go a little bit further and let's do it mathematics. And mathematics is this. Hubble constant, h squared, it's a square of the Hubble constant. It's the same as scale, the derivative, so velocity of the scale factor divided by scale factor. So distance between two galaxies, speed with which these galaxies move away, divided by the distance between them, squared. And it's proportional in these units where gravitational constant is equal to 1. It is proportional to the total energy density of matter, in which case it will be energy density of vacuum. Okay? Now I'm solving these differential equations. This is the simplest differential equation ever because it's constant. So this a dot divided by a is equal constant. It has this solution. Scale factor of the universe, so the distance between galaxies, start growing exponentially. That's exponent solution of this equation. No problem without this. With it, this is correct. And then, because energy density of empty space remains the same, it's given by this value of V, then the total energy is volume. Each of three dimensions grow exponentially. Volume grows like e to the 3ht. Total energy of the universe is a volume growing like that, multiplied by density. Total energy of the universe grows exponentially. Okay? So that was the idea of Alan Guth. If all of these later decays, then the total energy of particles there becomes exponentially large. Previously, if I start with 100 protons, I get 100 protons after expansion. Here I have with no protons. I have everything is vacuum. And then vacuum expands and expands, expands. And when it finally decays, I have extremely large amount of energy. Okay? And then from this energy, under certain conditions, exponentially large number of protons can be created. Okay, so easy. We can create the universe like that. Everything is beautiful, and this was a strikingly beautiful idea. Well, sometimes, however, if something looks too good to be true, then maybe it is. And so what was not exactly true in this theory? If the universe is empty, it's just vacuum, how could anybody even know that it expands? Okay. Now it looks like, well, this is just a silly question. Solve equations, get what you want. But the problem is that this empty energetic universe, it is what is called de Sitter space. And this de Sitter space was something miraculous from the very beginning. People debated it from this 1917 is the year when the Sitter space was first discovered, because there is a coordinate system in which the universe is exponentially expanding, this de Sitter space. And there is another coordinate system where in the beginning it was collapsing. And there is another coordinate system in which this universe is static. So if that is because there is no matter there. If I would see particles there, I would know that they are running away, but this would not be a vacuum. So that is this thing. And this was crucial for the crisis of the original idea. If there is no preferable coordinate system, then there is no preferable time at which this vacuum decays into the protons. And if there is no preferable time, then this decay happens in different parts of the universe at different time. And as a result, the universe becomes hugely, enormously inhomogeneous. And then it spoils all the beauty of the theory. We wanted to understand why our universe is so uniform, and we got this collision of bubbles, or whatever it is. We cannot get what we wanted. So we needed to break something in this nice picture. And first breaking was in the theory of new inflation. That is something which I managed to propose, and I was very happy about this, ecstatic, except for this theory died a year later. Okay. And then a year later, I realized, after being in horror, that my lovely theory also died just like old inflation. What can I do? What can I do? Best idea. Oh, okay. So it was possible to invent something much simpler. I considered a theory of a scalar field which has energy quadratically dependent on the scalar field. It's very, very simple. It's like if you have a spring, then energy of the spring is quadratically proportional to elongation of the spring. So energy of the scalar field is proportional to the square of the scalar field. Energy of electromagnetic field is proportional to E squared, and magnetic field is B squared. So nothing can be simpler than that. Consider this theory. Well, this is not electromagnetic field. If you have a, a scalar field, it looks like nothing. It affects you either by interacting you, by changing properties of particles as in the Higgs model, or by the fact that it has this energy, m squared, phi squared, it's energy of the scalar field. Now, if energy of the scalar field is large, like here it is at the top, okay? If the energy of the scalar field is large, then at that time the universe expands very, very fast. So let's see what happens when I solve equations of motion for this scalar field. And equations look like that. The first equation is very similar to what I have shown you. At the right-hand side is potential energy. At the left-hand side is the speed of expansion of the universe divided by the size of the universe. It's a little bit oversimplified equation, because on the right-hand side there's also gradient energy and kinetic energy of the scalar field. But if universe start inflating, then all of these other two types of energies, they rapidly disappear. And then another one is Klein-Gordon equation, is equation for the scalar field. So usually when you ignore expansion of the universe, you have it like that. Phi 2 dots is equal to minus m squared phi. And there is no second term here. But this extra term, 3h phi dot, appears because of the expansion of the universe. And if you compare it with the equation of a scale of a harmonic oscillator, then harmonic oscillator equation, look, the right term looks like the term here, and phi dot here have its analogy acceleration of harmonic oscillator, but there is a second term, which is a friction term, which is a viscosity. So it's like if you have a pendulum moving in a very viscous liquid. At first it may go fast, but then this viscosity slows down, slows down, and slows down. And the slowing down appears only if this viscosity or friction large enough. So when is viscosity for the scalar field is large? When it is large, Hubble constant. Hubble constant is large when scalar field is large. So when scalar field is large, then viscosity is large. If the viscosity is large, then scalar field does not move fast. If the scalar field does not move fast, then this term m squared phi squared remains almost constant. And then I have equation. A dot divided by A is equal to almost constant. And then it has almost exponential expansion. So that's all. Okay. So when looking back at this picture, when the scalar field is large, universe expands exponentially, then the scalar field rolls down, and the universe, the potential becomes smaller, friction term becomes smaller, scalar field starts oscillating near the minimum, viscosity is small here, and these oscillations produce normal matter. And after that, you have normal matter, but in the beginning, you have a stage of exponential large expansion, inflation. So that's it. You have a theory of harmonic oscillator. Nothing can be simpler than that. And it can explain everything that's going on here. And this theory does not suffer from the paradox which happened before, because it's not a vacuum state. It is a state where this Lorentz invariance or whatever, it's violated by movement of the scalar field. Okay, so you cannot choose coordinate system arbitrarily. Okay, so that is the main idea. So large scale field, large Hubble, large friction, and then you have inflation. And then you put all numbers together. You may start with Planckian size universe, size 10 to the minus 33 centimeter. Right now we see universe which is 10 to the plus 30 centimeters approximately, 10 to the 28, whatever. And mass, Planckian mass, 10 to the minus 5 gram. And then you wait 10 to the minus 35 seconds. So it's less than a billionth of a billionth of a billionth of a second. Bam! And the unit becomes this large. And because it is large, think about our Earth. If the Earth would be that large, then nobody would go to Everest for alpinism because it will be flat, absolutely flat. That's what makes the universe flat. That what makes it uniform. That's what makes it large. So many of the problems which bothered us are solved just like that. Okay? And then matter in the universe was born because this oscillating field in the end decays and produces it, and decays everywhere already at the same time, almost at the same time. That is an interesting part, that in different parts of the universe, the scalar field decays not exactly at the same time. Why? Because there were quantum fluctuations. Without quantum fluctuations, our universe would be empty. Quantum fluctuations make the universe inhomogeneous. And that was what was done by Chibisov and Mukhanov for the first time in 81, and then by several different groups of physicists in 82, and then many people checked all the calculations involved. But the basic idea is this. Even here in this room, we have quantum fluctuations. But they oscillate quickly, and after a while, you look around, and it's averaged to nothing. Okay, it's vacuum with tiny fluctuations. But in the expanding universe, you have tiny oscillating fluctuations. But when the wavelengths of the fluctuations become large enough, then it looks like homogeneous scalar field. But I've just learned that homogeneous scalar field does not easily oscillate during inflation. It freezes and moves slowly. So I have one oscillation, one wave, and then it expands, wavelength expands, and then another fluctuation, which previously was short wave, expand and freezes on the top of this one. Because when its wavelength becomes large, then it became like homogeneous field, it freezes. And then another fluctuation freezes on the top of the previous two. And as a result, in the homogeneous universe, you have inhomogeneous background of scalar field formed due to quantum fluctuations. Okay, this is the origin of large-scale structure of the universe. I remember how Mukhanov, who was sitting in the nearby office, told me that this is what we have. We have galaxies created from quantum fluctuations. And I say, you are crazy. This is impossible. There are quantum fluctuations, and these are galaxies. Okay, so, and then I learned and then I understand how it could be. And this is one of the shocking experiences in my life. And I am trying to convey this shocking experience to you. I think that I'm going very slowly. But maybe when I'm going very slowly, at least you'll understand some emotional background, not only physics. But how is that? What is so strange about this? And people often ask, so do you have any experimental verification of that? So for those who are interested in experimental verification, I've written here 10 different facts about inflationary cosmology, which are experimentally confirmed. And sometimes, in some cases, out of these 10 cases, which I listed there are about 2 or 3, where people were already ready to give up. So they seemed to them that they found that the universe is not described by inflationary theory because it contradicts something, something, something. And then after that, they found no, it was experimental data, something was in them. So there was several near-death experiences which inflationary theory experienced. So when some people say, oh, but do you have any experimental evidence? And I say, okay, here I have a list. And if you have a near-death experience, so this experiment could go this way or that way. And then depending on how it goes, for example, in addition to inflationary theory, there was a theory of cosmic strings, which was also possible to use for describing quantum creation of the universe. But then what happened? That the spectrum of fluctuations produced by inflationary theory, when you apply it to cosmic microwave background radiation, you see some characteristic peaks. And these peaks do not appear in the theory of cosmic strings and textures and others. So this is just an example, but for those who are interested in this, I gave here the 2 pages, and you'll be able to look at this some subsequent times. So what this we show you, this is a result of Planck, okay? And Planck, people from Planck, they have shown image of the sky, which they produced with small, small, small dots on this image. And they were coming to me and saying, we're so disappointed. We're all cities of United States, we're showing them this image, and nobody is excited. And I say, because they do not understand that what they see is on the scale of largest photographic scale ever, all the observable part of our universe. You see quantum fluctuations. This difference in colors is different in temperature, which appear because of quantum fluctuations in the early universe at 10 to the minus 35 seconds after the universe was born. They were born, they were frozen, and they formed the structure in the universe. So you see the universe when it was 10 to the minus 35 second young. Okay, that's something which makes me excited tremendously. And there are some graphs with these peaks, etc. And there are some recent graphs which summarize data from Planck satellite and then telescopes, ACT telescope, SPT telescope, and they put all of these points And all of these points, these blue points, are experimental results. And they're sitting exactly at the time, the place where theory predicted them. So it's pretty nice to have all of these evidences. It would be better than to have one more, because in addition to this fluctuation of scalar field, that was shown by Starobinsky and several other people also. There are also fluctuations of tensor field, gravitational waves produced during inflation, but they are weaker, and it's very, very difficult to find them. So we do not know whether we will find them or not, but if we find, then we would have 11th confirmation of inflationary theory. Some people ask me, so if they do not find gravitational waves produced by inflation, does it mean that that inflationary theory will have no experimental verification? I say, no, if they find it, it will be 11th verification. Well, this is something which was a picture popular in 2018, 2020, when the unified data from Planck and also from Bicep Keck laboratory. And they put constraints on this axis, constraint on NS, and that is slope of the spectrum of perturbations. And R is the ratio of tensor perturbations, gravitational waves, to the scalar perturbations. Okay, so experiments allow us to pick up not just that inflation is good, but they can rule out 99% of inflationary models, because some of them predict small r and some predict large r. For example, the simplest parabolic potential, which I've shown you, phi squared, okay, it predicts too large amplitude of gravitational waves. So first it was old inflation which died, then there was new inflation that died, then my simplest chaotic inflation died as well because of experimental data. But there was a Starobinsky model, there was Higgs inflation model, and there was a large family of alpha attractors, which Renata Kalish, who already was mentioned here, my wife, and I invented a long time ago in 2014. And they're based on the theory, give me any potential whatsoever. Give me kinetic term of a special type, which is a kinetic term specific for hyperbolic geometry in space. You know, our universe is curved, okay? So if space in which scalar field lives is also curved, hyperbolic, then interesting thing happens. That in canonical variables, this is original geometric variables in hyperbolic space. But in normal canonical variables, potential becomes a function of hyperbolic tangent, hyperbolic, right? Hyperbolic tangent of a canonical scalar field phi. A hyperbolic tangent asymptotically goes to 1. Independently of what you want, you cannot make tangent more than 1. So potential always approach some plateau. And predictions of the theory do not depend whether I start with quadratic potential or cubic potential or quartic potential or whatever potential. They always have the same experimental predictions. And these experimental predictions is what we have seen at the previous page. Here, oh, just a second. Here, or this happy blue area, which was satisfying experimental predictions, experimental results of Planck and others. This is exactly very close to what these alpha attractors also predicted, and magically, almost independent of the initial shape of the potential, if this happened in this hyperbolic space. However, life is never easy, and this is a result which was figures which were obtained after investigation the last year. Last year, DAISY, a separate experiment, which measured not exactly what this Planck and Bicep were interested. They studied something else, which is called baryon acoustic oscillations. And this is a different tool which helps also. You need to bring all of these tools together. So when people brought these tools together, something which Planck used and all these observations for cosmic microwave background study, okay, and results of DESI, suddenly they shifted experimental data with respect to scalar index slightly to the right. And well, this would rule out all these magic theories with hyperbolic geometry, which we loved so much again. So this is crucial. This is experimental science. No, it's not just science fiction with nice predictions and I can enjoy it and well, retire. Oh, I retired. I cannot stop working. Last year, with Renato, we have written 10 new papers. Okay, I just stopped teaching, but I continue working on this because it's so interesting. And yes, we can explain the new picture, but we do not know. Maybe we are too early trying to explain it because, in some sense, the data set described by Planck and other side, and the data set of DESI, they're kind of touching each other just slightly. They are marginally inconsistent at approximately 2 to 4 sigma. And when they try to unify uh, data which are not quite consistent to come to some conclusive predictions. Maybe it's too early to make any conclusions that this spectral index should move to the left, and then we need to discard the previous theories. But we are working. Okay, so we have this possibility that maybe we are in danger. Okay, so what we did? Well, we studied theory m squared phi squared. This is what I started with, the simplest chaotic inflation. But then I consider a model where scalar field non-minimally coupled to gravity, just one this term, nothing terrible, it's very simple theory. And instantly the prediction of the theory are exactly at the center of the new experimental data. So, this is a very nerve-breaking situation, but very interesting. This is where we live right now. And to move it a little bit further, if I study my original chaotic inflation and I add just two corrections to it, multiply phi and phi squared, then in this simple polynomial potential, I can describe any values of R and any values of NS just by fitting these three numbers, okay, and amplitude of fluctuations. There are three different data points: the amplitude of fluctuations, the slope of the spectrum, and the ratio of tensor to scalars. For that, there are three different numbers here. We can describe any data set. So it may be even disappointing. So we can describe anything, but we should not be, too relaxing, because with the quality of experiments growing with every year, more and more data are coming, and our life will be, this is, just about this picture, our life becomes more complicated, okay? Now, remaining 10 minutes, I wanted to tell you something which definitely will not fit into these 10 minutes. I will just tell you something and then I will show you whatever I will be able to. So the main idea of Einstein, which he formulated already in the late years of his life, he had written something which is called autobiographical notes, and he made an assumption about which he say, I would like to state a theorem which at present can be based on anything more than a faith. How is that? The Einstein theorem is just based only on faith, but on faith on some, well, that it is, everything must be reduced to something, and it could not be any other way. So coupling constants of nature must be the way they are, okay? And we can understand why the universe is everywhere the same, okay? Based on this principle. Well, now we almost did it because inflationary theory explains why the universe is everywhere the same, because we stretch the same patch, okay, and everything everywhere becomes the same. And why it is uniform, because it's stretching. And well, however, we find that it is not quite uniform because of quantum fluctuations. Okay, so we have something which we didn't expect. And then it is, uh, so we have uniformity of the universe explained by inflation. However, the same theory, because of quantum fluctuations, the same theory predict that in the different parts of the universe, it may be 100% non-uniform. Okay, so it's how we want to please our daddy. Okay, we want to if we realize the dream of Einstein, we'll be so happy. Huh? But sometimes we're happy if what we do is slightly different from what our daddy thought. So let's see what does it mean multiverse. And this is simple model. Start with the red balloon, then it becomes very large red balloon. Have inflation in this balloon, it becomes very multicolored, huge balloon. If we live in the blue part of the balloon, we look around, and this universe, everywhere I see, far, far away from me, it will be blue. By blue, I mean like water can be liquid and can be gas and can be solid. So I would be surrounded by sea with liquid water, and I will never see icebergs. Huh. But icebergs are possible. So there could be some other parts of the universe which were different, and we cannot see it because, well, we just cannot. They're far away from us. It's quite consistent with inflation theory. But then consistent does not mean right. So one may say, pessimist would say, if each of part of the universe is huge, we'll never see other parts. So it's impossible to prove that we live in the multiverse. Okay? And then optimist will say, if each part, repeating the same, if parts of the universe are huge, we'll never see other parts. So it's impossible to disprove that we live in the multiverse. And then you ask, indeed, can anybody prove that our universe must be blue? That is the idea of Einstein. We see blue, we see everybody, everything uniform. So can we really prove that everything is like that? Or maybe you are like captain on a ship, on Titanic. We moved to the sea because he didn't expect iceberg, and then they sink Titanic. So one must be more careful with predictions. And what Einstein said, I would rather be an optimist and a fool than a pessimist and right. And what quantum fluctuations say, they say that the scenario of a multiverse is more general because quantum fluctuations generate something which we did not expect. Okay, they can bring to life universes again and again because of quantum fluctuations there. This is something about eternal inflation, and I am unable to discuss this in any details, but I will just give you some examples. Okay, I have no time discussing cosmological Schrödinger cat. Okay, sorry about that. This is 1 hour. I thought that I will be faster, but this is an example. You have a theory, supersymmetric SU5 model, which was popular in the 80s, and it has 3 different minima of potential energy with respect to some very complicated scalar field. Okay, so in one of these minima, there is no difference between weak, strong electromagnetic interactions. In another minimum, there are no normal weak and electromagnetic interactions. And another one gives you, excuse me, give you exactly physics of our type. And then Steven Weinberg noticed that in the early universe, if the universe was hot, as the Big Bang story tells you, then we all must start in this SU5 minimum. And then we cannot jump to the minimum when we want to find ourselves. And then I looked at it and say, nope, no problem, because you have inflation. And inflation generates quantum fluctuations. And during inflation, you may jump from red minimum to blue, from blue minimum, excuse me, I guess my voice was exactly tuned for 1 hour. So you jump to green, and then because these parts of the universe continue expanding during inflation, then the universe becomes divided into pieces. In some of them, the universe looks red, in some it is blue, and in some it is green. And we can live only in green. So who cares if the parts of the universe have different color and we cannot live there? And then we make computer simulations of that. So we start by tradition, since I came from Russia, with a red minimum, and then quantum fluctuations start shifting me from one minimum to another. And gradually, the universe starts being divided into pieces corresponding to red minimum, to blue minimum, and to green minimum. And computer continue working, continue working. This corresponds to these fluctuations, adding to each other and pushing me from one minimum to another. And I call it Kandinsky universe uh, in, well, honor of the famous Russian abstract painter, who produced the pictures like that. But this was honest to God simulation of inflationary universe, which show how inflation continues and produce all of these magnificent pictures. So this is the kind of result of the simulations. In some parts, the energy density of the universe remains very, very high even now. In some parts, it already slowed down. We have our universe hot. We can live there. There are some parts of the universe which are red, and some parts of the universe are blue. And the distance between them is exponentially large. And you cannot move from blue to red. I mean, you might be able to do it, but you better not. Because particles, if you can live in the blue, you probably will be unable to live in red, because properties of particles change when you move there. Alan Guth said in 81, it said that there is no such thing as a free lunch, but the universe, inflation universe, is the ultimate free lunch. And this was at the conference in Cambridge, where I was impressed by free lunches which they served for the participant of the conference. So at that time, I said there, now we know that the universe is not just a free lunch, it's eternal feast where all possible types of dishes are served. Okay, and I did not expect this to be, well, so magnified by further evolution, by developments of string theory. So I'm jumping through anthropic principle, which I love, which I hated absolutely earlier because it did not make any sense. Universe built for us, okay? We live in the universe because God created the universe for us to comfortably live there. But it was just the universe by itself, made itself in all possible ways, and we live in the part of the universe where we can live, which explains correlation between us and the part of the universe where we live. Just like dolphins can live in the water, we cannot. So it's correlation, not causations. Dolphins do not create oceans. So there's no mysticism here. It's just normal science. And what was found later in string theory is that, and I'm, well, close to the finishing my talk. In string theory, people found, or maybe found, or maybe not exactly proven, but this the first attempt was done in particular in our paper with Kachar, Kalash, myself, and Trivedi from India. Okay, so we found a way to stabilize, possibly, some string theory vacuum. And then other people, Douglas in particular, found that the number of types you can stabilize vacua are colossal. And they calculated the total number of types of compactification of 10-dimensional universe, maybe many different. So they estimate that the number of compactifications is so large as 10 to the 500. Okay. Now, each compactification in practice means that we have the same string theory, but physics locally in the place where you live in the vacuum, if you are in this particular vacuum, is absolutely different from a different vacuum. Therefore, you really have a choice. You have 10 to the 500 different possibilities. Then people start calculating, and they found that maybe not 10 to the 500, maybe it is 10 to 1,500. Then they calculated more and say there may be also some continuous states. So then it is an infinite number of possibilities. Then other people came and say, no, we will prove that it's impossible to make any compactification of this type in string theory. String theory is a very complicated science. So we still do not know for sure where we are in this discussion, okay? But what is interesting that inflation, together with string theory, solve some problems which we could not solve previously. An example of this is why cosmological constant is so small. Okay, we knew that anthropic considerations would be able to explain why cosmological constant, the vacuum energy, is tiny. It is, as compared to natural units, Planckian, it is 10 to the degree minus 120. This is practically nothing, okay? So why cosmological constant, which was measured, I suppose, in 98 by supernova observations, why it is so small? Previously, we were trying to prove that it must be zero, did not work. And then it is extremely small. Explaining why it is small, much more difficult than explaining that maybe by some symmetry it's exactly zero. So what happened is that if it were just 100 times more, then galaxies would expand and we would be unable to live there. Or if it would be negative vacuum energy, then the universe would collapse and we would be unable to live there. Okay? And then, of course, you will say, but who gave you this tiny, tiny number? Okay? So then you say that you have any number from 1 from Planckian to -1 to -1 Planckian, but you have 10 to the degree 500 different choices. And therefore, there are lots of them which have lots, 10 to the 380 remaining choices which satisfy condition necessary for your life. So then it is physics, it's normal physics. And we can study this physics. And this was one of these times, there are several different moments in my life, when all of this was understood. It was just, and I don't know, we live like that. We do not know it for sure. Okay, so this is probably a proper time and place to stop my talk, even though I have lots more transparencies, but I am out of my 1 hour by 3 minutes. Thank you so much.
ये देखो इधर हरिदास तो ये तो अभी कोई आया है क्या? कुछ नहीं है।
Oops. Hello. Okay. Okay.
Professor Sami, I think Professor Linde is done with his presentation.
Yeah, so I was looking whether somebody is raising hand. So if there is any question from any participant and from all, हाँ ये दिख रहा है, दो लोगों ने रेज किया, कहाँ फिर कैसे देखें?
मिश्रा सर ने किया है, तो ये झंड के देख सो रहा है, और ये की हरिदास ने किया है.
Okay. So and well,
just a sec.
Professor Purification, maybe
just a moment.
you ask first.
Hello.
Oh, okay. Yeah.
I have a question from a particle physics point of view. So how should a particle physicist look at this inflaton, is it one of the elementary particles? If so, will there be other direct evidences for its existence?
Okay. I will give you an answer by an example. One of the inflationary models called Higgs inflation. Okay. And if the idea of Higgs inflation is correct, then the same Higgs particle gives masses to all elementary particles according to electroweak theory, and simultaneously play the role of the field which drives inflation. So it's just an example. There are not many constraints on the way how this scalar field can be constructed. There are some models based on supergravity where you can use supergravity to describe the inflaton field, and in particular, quite a lot of our work together with Renata College was about this inflation and supergravity. But Higgs inflation is the simplest example. The same scalar field which drives inflation, the same field later may break symmetry in electroweak theory.
Thank you.
Okay, Andy. Now, Professor Haridas, you have a question?
Yeah.
Yeah, so please ask.
Yeah.
Mute yourself.
I think Professor Haridas has already asked his question.
Okay, so who is the next? Panchpakeshan, maybe? Okay, okay. Please. You are muted, I think.
Yeah.
Yeah, can you hear me now?
Yeah, yeah.
Yes.
My question is about something which has come up recently called warm inflation. It doesn't want to go to 0 degree,
Yes.
and that way the parameters seem to be much more constrained and good. Can you say something about that?
Well, warm inflation is a very interesting idea. It would allow to, for example, when your potential is very steep and the scalar field falls down and loses its energy, like because of the friction creating particles or interacting with the thermal bath which exists here. This theory is a bit more complicated to construct, because it's like if I already have inflation even without any interaction with the background, then why do I need to do anything like that? However, if I would learn how to produce sufficient amount of particles which will take just a little bit of energy of this scalar field and slow it down, then it is a very interesting idea. And I know that several people continue right now developing it. So yeah, that's one of the possibilities.
Thank you.
Well, Rupa was trying to ask a question.
I had a few questions, Professor Sami, if you would permit me.
Okay, please.
Great. So thank you, Professor Linde, for an incredible talk. I just had 3 questions. I guess some of them or all of them might sound dumb, so please excuse me in advance. The first is like from whatever little I know, when you talk about this Cherubinski's R plus R squared inflation, I think the inflaton, the scalar field, is introduced as an auxiliary field into the setup. And please correct me if I'm wrong. And so that would probably, if that is true, that gives kind of an impression that possibly the inflaton usually should have a geometric origin. It should be derivable from geometry and not be considered as an independent scalar field. Is that sensible enough? That's my first question.
So the Stravinsky model is based on the theory which contain normal Einstein theory plus a term for R squared. So you have R plus R squared. Okay. Now you can make a change of variables and make change of metric to remove this R squared term, because working with R squared term is a little bit problematic. You do not know what is gravitational constant. Usually gravitational constant is something which stays in front of term R, okay? Now, if you have an addition R squared, and there is early universe, and you have classical R there. So you have R multiplied by R. So one of these R's, you say the constant, and then it is R which you vary, and another one of it. Okay, so it effectively renormalizes coupling constant, gravitational coupling constant, making it depending on curvature. So this is not very intuitively clear language. And what is possible to do, you make change of variables, rescale your metric, and rescale the also your scalar field, and then this term R squared totally disappears. And instead of that, you have normal gravity and scalar field with this potential looking like that. Okay, plateau, and then minimum and the hill. Okay, so when the scalar field moves along the plateau, then it falls down, etc. So this scalar field appears as a result of reduction of this theory R plus R squared to normal gravity plus something else. And Starobinsky called this field scalaron. But at the time when he introduced this theory, it was still not known that it is possible to do this trick. This trick took 7 years for actually made by somebody else.
So, I mean, like, for example, I mean, I'm basically a string theorist, so I guess this sort of supports the idea that the inflaton should usually be derivable as some kind of a modulus in the theory coming essentially from the internal or from the compactification scheme, rather than being an independent field in the theory. Is that right?
Well, it is possible. I would not claim that it is necessary. Okay. We don't know. It's possible because physicists are divided into different clubs. Some of them believe that string theory is a proven theory of everything, and the space-time is 10-dimensional. Some of them also think that maybe it is 26-dimensional. Okay, so and some say that in addition to that, you may just have physical scalars. So maybe all scalars are the result of reduction, or maybe not. I don't know whether it's necessary to make this assumption or not, but it's a legitimate assumption.
Professor Sami, do I have the permission to ask 2 more questions, or no?
Of course.
Professor Sami, can I ask 2 more questions?
Yes, please do.
Okay. I'm curious about this. So there was this choice. I mean, there was one of the potentials where you had fractional powers of phi coming as multiples of 1/3. What is that about?
Fractional.
I know Kachru and friends probably had worked on this a while back, if I'm not mistaken. But what is that? What's the story behind powers of 1/3?
You probably are thinking about the string theory motivated model by Ivo Silverstein, who is a wife of Shamil Sachs. Yes, it's called monodromy inflation monodromy scenario.
Oh,
it
that's
is a very
Silverstein. Yeah. Silverstein's, I guess.
Yeah.
Oh, I see.
Yeah,
okay.
Yeah, and that was a very interesting idea with the potential with certain periodicity in it. It's quite possible. Why you get these things 1/3? Actually, what they had first, just potentially effectively linear, and the second model which they found is phi to the degree 2/3. They did not study. They didn't find phi 1/3. You sometimes will find this phi 1/3 in the pictures of experimentalists. But experimentalists just write whatever they can consider, let's just write, okay? But from Eva's theory, they were either linear or 2/3. How they obtain this 2/3, it's a string theory construction. I would not easily reproduce you the derivation. And I asked her, how is that? If it is phi to the degree 1/3, this means that potential just boom, like that, falls down, does not have any minimum. No, it's 5/3, phi to the degree 1/3 only asymptotically. And when it goes down, it becomes normal quadratic potential, okay? So it's quadratic, and then phi to the degree 1/3 asymptotically.
Okay. My last question is it true that in your theory of inflation, the inflaton is transplanckian? I mean, there is this, people talk about this excursion problem. What is your take on that?
Okay. So first of all, there are some models where the inflaton is subplanckian. So you can just fall from a special hill and then do everything that you want. If you study simplest model of chaotic inflation, then scalar field can and often is superplanckian. So it has a value larger than Planck mass. But the question is whether it is dangerous or not. And that is the question which depends on how you interpret the scalar field. If you just study it as particle physicist, then you say, in particle physics, like Higgs model, the physical quantity is scalar field multiplied by coupling constant. It gives you the masses of particles. So masses of particles better be smaller than Planckian, okay? But then if you make this inflaton interacting with matter with very small coupling constant, let it be absolutely huge. It does not induce any large masses to particles, so that is not a problem. What would be a problem if the scalar field, as you suggested, has geometric origin, okay? Now, in geometry, depending what kind of geometry you're dealing with, there may be some constraints. And this is something related to this swampland conjectures by Waffe and others. Okay, so in some theories you can prove this swampland conjecture. In some you cannot. Okay, so you must distinguish whether it is a general conjecture or it is something which was kind of proven for some kind of axion fields under some special conditions, or Waffe thinks that it is generic. And now there is another interesting part of the story, which was a lesson for me. Okay, I was at the talk by Qumran Waffe, and after his talk, I asked him, "May I ask you a $1 billion question?" I say, "What do you mean?" Just a $1 billion question. Okay, so depending on that, $1 billion is it to be spent or not? So, is order of 1, if the object of order 1 is 10 to the minus 2, so 100, is it of the order 1? And he looked at me like that and said, well, if it is 10 to the minus 10, it is not of the order 1. That was his answer. Okay. Why I asked him this question? Okay, because these quantities like R and the number of folding, etc., they depend on V prime potential derivative of the potential divided by V. And his conjectures are that these quantities like V prime divided by V or V2 primes divided by V, they are of the order 1. So if 10 to the minus 2 is impossible, then people should not spend billions of dollars trying to find R, this tensor to scale ratio, because it is small only if this ratio is, well, 100, for example, okay? So if it is 100, if it is forbidden by what Wafa said, then no need to spend $1 billion, you can save money. Okay? So his answer was 10 to minus 10 is not of the order of 1, because he is a mathematician, okay? So he makes statement of the order of 1, assuming that maybe it is of the order of 1, or maybe just a number, but not 10 to the minus 10. So about 10 to the minus 2, he does not answer. But for physics of inflation, this is a huge difference.
Okay. Right. Thank you. Thank you.
Okay. So, okay. Okay, please ask. Mute yourself. You are muted.
Okay, I guess everybody else right now at the lectures, because it's the
Unmute.
morning time. Okay, I am very grateful for your interest and for inviting me. And yes, good time for celebrating. Yes.
Andre, I have a small question.
Yes.
I have a small query. See, sometimes people speak about the initial condition problem of inflation, like
Yes.
Steinhardt with his colleagues on numerical gravity. They're trying to argue that the probability measure of generic initial conditions that would lead to inflation is very small. I do not much understand it because this for me is a black box in numerical gravity they did. So what do you think about these claims? You
know, I'm afraid that this is a sociological issue, not the issue of physics. And it just, but I try to, okay, I will answer you this way. Recently, for example, they issued a complicated mathematical calculation proving that inflationary conditions in my simple m squared phi squared model are unrealistic from their point of view. So model m squared phi squared, I know which initial conditions are necessary for it. So scalar field must be approximately at least 15 times in this particular model, okay? 15 times larger than m Planck, and that was discussed in the previous question. Whether it is better, whether it's good, in different models you have or not have this constraint. But in this particular model, we have the constraint. So if you ever studied chaotic inflation, you know that you must start with scalar field larger than approximately 15, and after that you make your calculation. So they published a paper, which is very, very heavy work. I know that it was not Paul Stanhope who did this work. They had two collaborators who are very good in numerical relativity, so they did the job which they wanted to do. And they studied very general initial conditions with extreme anisotropy of space and with extreme inhomogeneity, okay? And with potential energy of scalar field, which was assumed to be much, much smaller than this extreme inhomogeneity and extreme anisotropy. And after they studied it, they found that inflation in this model is insufficiently long. So they did not find that there is no inflation. They found that it's insufficiently long, okay? Now I checked, what are exactly initial conditions they studied? Well, they assumed that scalar field begins at value 12.5. So if they read the papers on chaotic inflation written 40 years ago, they would know that they need to start 15. They chosen to start with a field with which all of this anisotropy, how Americans say it's red herring, it just have no relation to the problem. They say that it's because of the inhomogeneity. Where they say that other people, all of them, disagree with what he said, find that it is possible initial conditions, normal and not problematic. He is finding them that they are problematic because they said the other people did not study sufficiently generic initial conditions for anisotropy. So what you look at the paper and you even remove this anisotropy, you do not have long inflation because he have chosen initial conditions for which what he knew. He is educated person. So why did he choose initial conditions for inflation to fade? Nobody would. I knew that this is the source of the problem, but others would be unable to check because it's super complicated general relativity calculations. Only few people can reproduce them, but they were made specifically under conditions for which all this anisotropy is just irrelevant. Okay, so what? I don't know, and that's unfortunately something which I see all the time. It's beats me.
Okay. Andrei Dimitrievich, what is your view on bounds?
On what?
Bounds, cosmological bounds. Some people, sometimes people think bounds as alternative to inflation and
yeah. Okay, so again, maybe you better stop recording. Yes, but cosmological bounds in general is a very interesting idea. In general, it would be great to, instead of singularity, have some way or go through the near the singularity. So it's tremendous idea, and many people whom I very respect, they continue studying this, and this is very interesting option. In 2000, I think it was in 2000, we received a paper by Paul Steinhardt, Neil Turok, Overott, and Khoury, which was called ekpyrotic theory, whatever. They found bounds. They start with a theory with two brains interacting with each other, and after that they have Big Bang, and you solve all problems in the context of string theory, and homogeneity problem solved without inflation because of the bounds. And we looked at this is very, like 70 pages, etc. Renata looked at it. She is an expert in supergravity and string theory. And she said, look, this is very interesting. If it is so, this will be a tremendous story. So and we start reading it. I'm reading it and I say, Renata, look at it. What is that? They assume that these brains were exactly parallel to each other, and the universe, therefore, is by construction absolutely 100% homogeneous. After that, they say that this solves the homogeneity problem. How is that? If you assume that the universe is homogeneous, how does it solve the problem? She reads further, and look, this part about the string theory of brains, I do not understand it. Can you look that? So after about an hour, we see that the whole paper just, doesn't work, okay? We have written a paper after that, 2 months later, checking everything, etc. And we have written a paper. So the paper was called Pyrotechnic Universe. And the paper was ekpyrotic. And we have written pyrotechnic, like a joke. And we explain this is an error, this is an error, this is an error. After that, other people found an error in the way they calculated density perturbations. So they present claimed that the perturbations produced in their mechanism is the same like in inflation, just with slightly different tilt of spectrum. And this was wrong. They were fighting for that, and everybody found later and agreed that they made a mistake. Then we checked what happens when these brains really collide. And their statement was that after collision of the brains, there is a big bang. And when we analyzed the equations of that, we found that it is big crunch. It is a collapse of the universe. So when professor of this rank cannot distinguish expansion and collapse, what can we say about that? So then they understood that they have a problem with collapse. And they say, okay, so now we will show you how to go through the singularity. They've written a paper on the language of string theorists. The second paper, after they already realized that the original statements of the first were incorrect. Okay, they've written a second paper which explained how you go through the singularity. And then string theory community analyzed and said, no, your conclusions are incorrect. And then they continue writing after one paper after another, one paper after another. In the next one, they improved error of the previous one, but contained some problems which they promised to be solved in some other papers as well. So this, after like maybe 10 years of following and finding one error after another, I stopped following. It's just like that.
Well,
You
thanks.
ask, how is that? How could it be?
Okay.
I
Well,
also don't know.
Well, thanks a lot for these clarifications, because the papers
What?
are so, for these clarifications, because the calculations are so involved, getting into those, whether my students who are interested, getting into the not clarifying. So thank you very much that you clarified this issue. It is not just for a question, because the students were working and finding issues. Okay. Thank you very much. So,
Yeah.
Andrei Dimitrievich, we are very thankful to you. I had seen you long back, is what, 81, just in Moscow. After that, I never met you. Okay, so I just saw you, and Hawking was there, visited Moscow, and you were trying to convince him on your scenario. Okay, that I remember. Okay, thank you very
Yeah.
much.
Well, thank you very much for inviting me.
Okay,
You know, I'm from Russia, and in Russia there is a natural, deep-rooted, how to say, respect for Indian thought and Indian philosophy, and yeah, it influenced myself very strongly. Not just physics, but the history of Indian thought. Okay, so.
Okay, thank you. Thanks a lot.
Thank you very much, and well, great to see all of you at this particular day.
Thank you.
Okay,
goodbye.
Okay, so I think so that brings us to the conclusion of this session. And again, thank you so much to all the participants, and of course, obviously the speaker, Professor Linde. It's past 10 o'clock there, so grateful that you decided you were able to give this talk. Probably inconveniencing yourself, but thank you, and thanks to Professor Sami for chairing the session. Though I think we have formally ended the session, I see that there are a couple of questions on the chat. I would just for the sake of completeness, so one of them I feel compelled to to just bring to your kind attention, because that is a question by one of our former students who's also the web designer. So I don't want to make him angry. So it's a question about what is meant by vacuum decay. That's the first question. And the second was by, not by him, by Professor Kaushal, which is essentially implying what caused the Big Bang? What was the reason behind the Big Bang? So if you could shed some light on these two, be very kind.
Yeah.
Otherwise, we can end the session.
Well, vacuum decay is a relatively simple thing. So suppose you have just an example, this Higgs field. If Higgs field Higgs field has energy depending as a function of the value of the field. And this function may have some additional minimum at large value of scalar field. Okay, so then if you, by some history of the universe, would find yourself standing in this minimum, which was called false vacuum, you'll have very large vacuum energy, and then you want to transit to the lower energy, just like you want to fall from the hill, roll down on the bicycle, okay? But you cannot because it is separated by the barrier. So this decay occurs by formation of bubbles of a new phase, like a new vacuum, surrounded by the old vacuum. It's like when you're boiling water, you have bubbles of vapor surrounded by liquid, okay? So when you were in this false vacuum, this minimum at high energy density, you may create a bubble, it's quantum mechanically formed bubble, so that energy density inside this bubble is smaller than outside, and it expands. So that is how you can understand vacuum decay. Now, as for what was before the Big Bang, this is really a very complicated question. And that is something which goes beyond just inflationary theory. Suppose if you assume that the universe was born, or when it bounced, whatever it was before, it does not matter. If after whatever was there, you are in a certain state with the properties which are required for inflation, then we have everything else as needed. You can have inflation after bounce, no problem without that. You can have, but what happened before this? And at this, I would ask the question, what do you mean before? If there was no time before, if we start with something, how one of the philosophers said there was no time before God created the universe because the time itself was also created by God. Okay, so but on a less religious tone, I was playing with solving wave function equations for the wave function of the universe in the toroidal universe, and what I found that you can it describes creation of the universe from some state where it should be interpreted as creation. I don't know, but it looks like normal time with oscillations, matter, reheating, etc., appears after some stage during which, when I'm solving this equation for the wave function of the universe, during which there is no oscillation. So when I'm going back in time, I see there is something oscillating. So it's like clock ticking, and I'm going further and further back in time. I see it's time is here, it's still ticking. And then I'm going closer to what I call maybe beginning of the universe. Suddenly it's no longer ticking. So it's not that there was a time without the universe, but when you go back in time, there was no ticking. Okay, so we are all presumed somehow that time existed before and the universe appeared. There's something which we do not understand yet, and if you ask it to me really seriously, because there are something which I deeply do not understand, and this deep not understanding, maybe there's something in it. If you do not have any observers in the early universe, there was no observers. no clock, nobody like we. Does it mean that the universe existed before we were there? Or it's kind of mathematics consistent with the possibility of existence, and existence is only when we are here with our consciousness? And is it true that consciousness is just a product of matter? So I don't know. I'm just saying that this problem of what was before the singularity is as profound, but maybe less profound than the possibility where I was before I was born.
Okay, I think if there are any further questions, because we are already running late, so one can always email Professor Linde, and so let's conclude this session definitively. And thank you once again, Professor Linde. I guess for the second time. So yeah, that concludes the morning session. That is. From India, the morning session, and we would be reconvening on a different Zoom link post-lunch for Professor Gerard Toft and Professor Robert Wall thereafter. So have a very pleasant day / night / evening, whatever part of the world you'll be logging in from. And thank you. Bye-bye.
Thank you so much. Very pleasant to talk here.
Thanks. As always, thanks to the student team, Shivam Singh Aswal, who's also, despite he's working in some company, but he's still taking some time off. And Rupa Pramodhan, our student, was sitting here in my office since morning, helping me out with little details. Thanks. God bless as always. And bye-bye. See you soon in the afternoon. Bye. Stay safe.
Okay. Goodbye.
Bye.
Bye.